right, we're back for another discussion about irrotational flow. Today we're going to talk about the doublet. So the objective of today's lecture is to use those building blocks that we discussed last time and derived last time and build up one of the more complicated solutions, the doublet. Now the doublet itself isn't that great, but it's often used in conjunction with uniform flow and so forth. So the doublet, as mentioned here, is the combination of a source and a sink. And the Rankine half body, which I've showed you before, is the combination of a uniform flow and a source. And then the Rankine body, or flow around a circular cylinder, is the combination of the uniform flow and the doublet. So we need the doublet in order to derive this Rankine body. All right, so what's a doublet? Well, it's a jacket. It was worn in the 1600s by some kings and things. No, I'm just kidding. A doublet is not a jacket in this sense, in this class at least. A doublet is the combination of a source and a sink, and they're initially separated by some distance, plus or minus eta. And then what happens is we let that distance go to zero, and it induces a flow. It's basically, you can see that it circles towards the source on the left and then back into the sink, and likewise it's mirror imaged on the bottom. So it generates this flow field or this set of streamlines. That's what the doublet looks like. One would think that if you superimposed a source and a sink you wouldn't get any flow at all, but the math is quite different. So, and thank goodness for that. So let's have a look at the math. The mathematical description of the doublet is the superposition of a source and a sink. So this is one of the first examples that we have where we have superimposed two solutions to the Laplace equation. So here's our source separated by a distance eta minus eta, and here's our sink separated by a distance plus eta. What we do is, when we bring these two together, is we let eta go to zero, but we have to, in order so that it doesn't annihilate itself, that the source and the sink don't annihilate themselves, we have to let the strength of the source and sink, basically the volumetric flow rate, go to infinity, such that this product, epsilon times V naught, remains constant. And that's basically what saves the day. If it wasn't for that, then the doublet would annihilate itself. So this is the basic form, and here is the combination as far as the potential function goes. And we take the limit of this as eta goes to zero, and the flow rate, the volumetric flow rate, goes to infinity. And one can show that this is what you get. Now, this is, I think I'm going to let you actually do this. You can find it online or in textbooks if you would like, but I think it's a nice exercise to let you do this, this limit. I would say it's a 2-bean level of difficulty. Get yourself a cup of coffee and have at it. And it's basically just some trig. You got to crack this natural log open and have at that. All right, so once you get that done, you can write your doublet in terms of the stream function in Cartesian or cylindrical coordinates, or in terms of the potential function in Cartesian and cylindrical coordinates. You might have seen the doublet as a dipole. It's also known as a dipole. It's that model of the magnetic field around the poles of the Earth. And so again, you know, the Laplace equation describes lots of different kind of phenomena, physical phenomena, magnetic, electromagnetic phenomena. So it's not surprising that these solutions are rehashed in all kinds of different physical fields. All right, that's the doublet. Next time we're going to work on the Rankine half body, and we'll see you then. All right, thanks. Bye.